Aaron Naber from Northwestern University, and he's going to talk about the L2 curvature bound on space with bounded Ricci curvature.
Thank you very much, and thanks for the opportunity to be here again. Let me first promote something. So in the spirit of this semester program in MSRI, there's another one coming in 2017 in Toronto. I have been asked to promote this, so it will have some workshops in some summer schools and some positions that you can go for. So if you look at either on the web page, which you can get either by asking me later for it, or if this is the YouTube video, you can just pause. You can go to the site and find out more. So okay, so this is a joint work with Wen Shui that I'll be talking about. The talk is focusing on the regularity and estimates for spaces with bounded Ricci curvature. In particular, sort of our main estimate that we'll discuss is to prove that if we have a manifold and if it has a bounded Ricci curvature and a lower volume bound, then automatically you have a priori L2 bounds on the curvature. Right? So I'll talk more about that, but if you sort of recall, right, I mean, in either in the four-dimensional case, well, I mean, I did this with Jeff before in the four-dimensional case, but the relevance there was that people in the 80s used to assume things like Euler characteristic bounds, topology bounds to get this, and the point is it's for free. And similarly in Kähler manifolds, I mean, you can get an L2 bound globally if you assume topology, but now it's for free. You don't have to assume second Chern class bound; you actually get it automatically. In fact, you get local ones, as we'll discuss, so it's actually much stronger. No, that's what I just said, right? So I'll say that in more detail later. And another sort of result that comes along the way is to prove that for limit spaces, manifolds with lower volume and bounded Ricci curvature, the singular set's n-4 rectifiable with uniformly finite n-4 measure. It's sort of worth mentioning, actually, that you kind of have to prove this first before the L2 bound. And even more precisely, you have to actually prove them all at the same time. They're kind of linked together, and there's an iteration argument where you kind of wrap your way up until you can kind of cover everything. But we'll kind of get to that, hopefully. So kind of an outline of the talk. I'll mention some preliminaries on Ricci curvatures and limit spaces, especially for the graduate students in the audience. We'll talk a little bit about background and previous results in the literature. I'll spend a little bit of time then actually saying with some precision what the actual results are for this talk, and then we'll outline the proof. So there's a few new ideas that are necessary in the proof, but they kind of all have sort of a common theme, which is that of somehow getting sharp estimates on what we call neck regions. And we'll say this more precisely, but there's a few new estimates along the way that are actually quite strong for harmonic functions that you have to prove that are new on spaces with bounded Ricci. I mean, you need the bounds actually to get the estimates. So background, here's sort of the standard spiel I give at the beginning of a lot of my talks. So we're going to talk about some Riemannian manifold, maybe a pointed Riemannian manifold, if you have some point in there. The curvature, if we're all kind of familiar, right, it's a four tensor, and you can define it as being the antisymmetric part of the Hessian of a vector field. The point being that on Euclidean space this vanishes, on a manifold it doesn't. If you want intuition for curvature, this is awful. This tells you nothing, right? The way one should really think is that this is like the Hessian of the metric. Right? So when people say we have bounded curvature and therefore can control the space, it's because it's like having a function with C2 bounds and you can control the function. Right? I mean, this is basically what it comes to, and the intuition as to why bounded curvature means something and gives actual control. Likewise, right, what's the Ricci curvature? It's the trace of the curvature. And that means if we're interpreting the curvature as the Hessian of the metric, it means we're really interpreting the Ricci as the Laplacian of the metric. I mean, in some spirit, Laplacians of functions appear absolutely everywhere, right? So it's not surprising that in geometry, then what should take the place of the Laplacian of a function should appear everywhere as well. This is why Ricci curvature somehow just magically appears wherever you go in the subject. Okay, so we're going to want to study limit spaces with lower and bounded Ricci curvature. Where these limits are going to be in the Gromov-Hausdorff sense. So that is, we're going to have a sequence of manifolds, and they're going to converge in some sense to what's only going to be a metric space. I'm not going to define for you what Gromov-Hausdorff topology is, but let me just say in words sort of how you should think. A definition would just be more confusing than helpful if you haven't seen it. It's basically like L-infinity convergence for functions. Right? So what that means is that if you have two functions and they're L-infinity close, say epsilon close, that means, everywhere, I mean, they look pretty close until you look too closely, right? I mean, in some sense, once you start zooming up beyond that epsilon, it tells you absolutely nothing about the behavior anymore. But until you get to that point, it's very accurate, right? That this is basically what Gromov-Hausdorff is, right? So if you want more on a function, you need things like C1, that's that kind of C on all scales, and L infinity doesn't do that. In the same way, Gromov-Hausdorff sort of sees at some scale, but not all scales. The reason it's important is that Gromov proved a really amazing thing. He proved that if you have a sequence of manifolds with a lower Ricci bound, you have compactness. This is why you define notions of convergence. If you don't have compactness, it's not useful. He showed that if you have a sequence of spaces with lower Ricci bounds, then automatically you can take subsequences that will converge. That makes it make sense to actually talk about limit spaces. I mean, if you didn't have a compactness theorem, you're kind of just making up a notion to study. So since it makes sense to consider limits, it became reasonable at this point to ask, what do we know about such limits? And this was sort of what initiated the study to one degree or another. So what's the structure of such limits? In fact, I mean, you know, the main results of this talk are really about, one of the main results is about manifolds, but these things are connected. You can't really separate them. If you want to understand the manifolds, I mean, the way this usually works is you end up proving by contradiction, right? So you end up getting sequences of manifolds, which inevitably leads you to a sequence, and you try to some limit space, and you get your contradiction by studying the limit space. So even if you want to know the manifold structure, and you don't care at all about singular spaces, you're stuck doing this, right? In the same way that this happens for functions, and you take sequences of functions. So what we're going to focus on here is going to be sequences of spaces which have two-sided bounds on Ricci curvature and a lower volume bound. What's this morally mean? It basically means our limit space, X in this case, itself has bounded Ricci curvature in some weak sense, which you don't bother to define because it's coming from a sequence of guys which have bounded Ricci curvature, and that the limit space is n-dimensional. So it's basically saying that your limit X is an n-dimensional space with bounded Ricci curvature. That's what these two assumptions really come down to. The study of such things really began in the 80s. And the main theorem that was kind of the consequence of a lot of work during the 80s was the following. Due to lots of people. I'm sort of taking a lot of their theorems and combining them to what you get at the end of it. So take a sequence of 4 manifolds which limit out. And let's assume a little bit more. Not only are you going to assume the Ricci's bound and there's a lower volume bound, but they wanted to assume there was a diameter bound and a topology bound on the sequence. Because then what they were able to conclude from this was that the limit was a Riemannian orbifold with isolated singularities. It's a nice result, right? So it's basically a 4 manifold away from a finite number of points, and those finite number of points have basically a simple, I mean, if you try to think to yourself, what's the simplest sort of, structure of a space which isn't a manifold, you're going to go to orbifold. And what's the simplest orbifold? Well, isolated singularities, right? So this is as close to being a manifold as you can get without being one, right? This is the next most complicated thing. Okay, but this led to a few points, right? So I mean, this was right around the time when this codimension 4 was conjectured, right? Because, I mean, well, what's a 4 manifold with the singularities are isolated? Well, it's codimension 4, right? So the guess at this point was that this should actually always be true. Limit spaces should always have singularities which are of a codimension 4 nature. Note, it wasn't even proved in dimension 4, right? Because to get it in dimension 4, you have to assume topology bounds. And this is somehow non-trivial, because somehow if there was a counterexample to that, it should have been in dimension 4 already. Jeff and I showed that, I guess, maybe about a year and a half ago, but what I really want to focus on actually are the consequences of that. Jeff talked about that before. So one thing you get once you prove this codimension 4 is the following. So if you combine, once you know you have codimension 4 singularities, with the notions of quantitative stratification, don't worry about what it is, sweep it under the rug, you can prove the following about manifolds, right? Nothing about singular spaces and the rest. You can prove that if you just have some manifold with bounded Ricci curvature and a lower volume bound, then at least for every epsilon, we could show that there was some constant such that the Riemann curvature was automatically an L2 minus epsilon. So you get this sort of nice consequence for smooth manifolds. You do, in fact, have to prove this codimension. So this is what I was saying about contradiction arguments. In a sense, you do have to prove this codimension 4 result first about limit spaces before you can actually prove this. Okay, so we did slightly better in dimension 4. So in dimension 4, we basically could cheat and use the Gauss-Bonnet formula in the opposite way that people did in the 80s. In the 80s, people would say if you have topology bounds, then you use that to get the L2 curvature bound from Gauss-Bonnet. That's really why they assumed topology in dimension 4. Once we knew codimension 4, we could go the opposite direction. We could actually prove topology bounds and then stick that into Gauss-Bonnet to actually include an L2 bound on curvature in dimension 4. So this is sharp, by the way, L2. It's very easy to rig up examples where you can't be in better than L2, right? So L2 is as nice as you hope to get for spaces with bounded curvature. Right. So from this, right, what one gets actually is that the topology is automatically bounded. This was a conjecture of Anderson. And that actually you can just take four manifold limits now with just the bound that Ricci and lower volume bound to get the orbifold conclusion. Okay, so that's background. All right, good. So what's left? Oh, yes, right. It seems sort of natural from this to conjecture the L2 bound, right, in all dimensions. I guess I did this in my ICM talk, and we did this in the codimension 4 paper. But past that sort of, I mean, what else was sort of open? So it's worth mentioning the following about the proof of the codimension 4 conjecture that Jeff talked about earlier. It says, I mean, to prove it, you never say anything about the codimension 4 singularities. We never study a thing about them. We study codimension 2 singularities and codimension 3 singularities, and we study them well enough to say they actually don't exist. But we never say anything about codimension 4 singularities. Fundamentally, this is why we can't get that L2 in higher dimensions. You've got to actually push up and say something about the codimension 4 singularities themselves to understand the space well enough to say stuff about this. In particular, other questions that kind of float around for this is, besides actually, being codimension 4, I mean, Cheeger and Colding in the mid-90s conjectured it should have finite n-4 measure, or sort of a reasonable thing. This was sort of a reasonable refinement to the codimension 4 conjecture. You also might ask things, does it have a bi-Lipschitz structure? What kind of structure does the singular set actually have? And these things were still sort of unknown, as I said, because I mean, our techniques really couldn't analyze codimension 4 itself, just codimension 2 and codimension 3. So now we actually get to the point of the talk. So the main result of the talk today is to prove the L2 bound. So together with Wen Shui, we showed that if you have a space and if it has bounded Ricci curvature and a lower volume bound, then automatically there's some constant such that the L2 curvature is bounded in all dimensions. It's pretty easy to see that, right? As I said, this is sharp. I mean, sort of standard examples with singularities will show that 2 plus epsilon, it just blows up to infinity pretty easily. I mean, you can't control this. A nice little corollary is the following. So let's take either on a real manifold, the first Pontryagin class, or on a Kähler manifold, the second Chern class. Well, what's known in Kähler geometry, right? If you have a compact Kähler manifold with topology bounds, meaning second Chern class bounds and first Chern class bounds, and you're looking at something which is, say, Einstein or bounded Ricci, you could prove the L2 bound globally, right? Now, a consequence of this is the fact that you don't have to assume the second Chern class is bounded. It automatically is. You get this for free. In fact, not just globally, it's a local result. I mean, you have second Chern class bounds on every single ball that are scale invariant. So if you look at any ball and you integrate the second Chern form, you've got a bound on it. Same with the L2 curvature. So even in the Kähler case before, even if you had a global L2 bound, that doesn't mean you have a scale invariant L2 bound on every ball. It can degenerate in all kinds of ways. You just can't control that. But now you see these are automatically bounded. Same with the first Pontryagin class in the real case. Oh yes, and some similar estimates if you just sort of want to push the ideas for the fun of it. You can also get the gradient if you're Einstein now, so not just bounded Ricci, but you add the extra Einstein condition. You can get the gradient is in L4/3 and the Hessian of the curvature is in L1. These are also sharp. Basically proved by the verbatim methods that I'll show. Okay. So the second main result that I'll discuss, and this is in part because it's somehow you can't avoid this result in the proof, is that we can show some structure on the singular set of limit spaces, which is at least semi-interesting in its own right. So what we show is the following. If now take a sequence of Riemannian manifolds that have bounded Ricci curvature and a lower volume bound, and let them limit to some space x, then let's look at the singular set of x. This is literally, you can just take the set of points which aren't manifold points. Everything else is a nice manifold, C1 alpha manifold point. Then for starters, it's not just in -4 dimensional, it's actually in -4 rectifiable. For those of us who don't know what this is, just think in -4 manifold away from a set of measure 0. The subtlety here being is that the measure 0 set isn't closed, right? It can be some scattered everywhere set, but this is roughly correct. And you get a finite volume estimate now. So this was sort of the other sort of conjectured result from before. You do get the singular set isn't just in -4 dimensional, but it has finite in -4 volume on each ball. And also, by the way, from this, you get that for almost every point of the singular set, the tangent cone is unique and isometric to some nice orbifold things. So it's Rn -4 across R4 quotient some action on it. The gamma is freely acting. I'll draw pictures of this 3 later because it'll come into play in our definition of neck regions. Oh, and that's what I said about singular sets. I may repeat a little bit what comes later because I plan on eventually putting this on my web page once I actually, the paper's actually out. We're on page 72, and I'm hoping it's not going past 80, so the paper should be done soon. Okay, so now results are done. We actually start moving into stuff. Most of the proof now, it's analysis now, and the analysis is going to take place in something called the neck region. And if I give you the definition straight away, you'll dislike me a lot. It looks very technical. But it's one of those things that somehow, there's a very clear, intuitive notion, and if you try to make it rigorous, this is what you'll end up with, right? So after 15 minutes, it's clear, but the first 15 are painful. So instead of giving you the definition right off, I'm going to give you some examples. And basically, the definition generalizes the example. So what's somehow the easiest notion of a neck region? So let's do the following. And maybe more precise would be to call it an N-4 neck region, but whatever. So let's consider the following, which is actually going to be kind of a singular version of a neck region, which does appear in the paper but won't actually appear here, but it's actually a little bit more intuitive, so we'll think of it this way. So let's look at our space here, which is actually going to be Rn-4 cross, let's say, C2 mod Z sub 2. So here's our C2 mod Z sub 2. So it's a cone space, right? It's just a quotient of Euclidean space, a little cone here. And here's our Rn-4 factor. And neck regions will always be defined on some ball. So let's, here's there's our factors. So let's pick some point and look at a ball. Maybe the ball of radius 2, whatever. And let's look at this ball of radius 2 here. And let's decompose this. Right? So there's sort of there's two sort of canonical pieces kind of floating around here, right? There's a manifold piece up here, and there's the singular set here. The singular set is the Rn-4 across the origin here, right? Because you've got this cone singularity at this point. So it would simply be pretty canonical to simply split our space up into those two pieces. And the way I want to write that is I want to write this as being an N union S, where S here is going to be just the singular set Rn-4 across the origin, maybe intersect the ball of radius 2, and in here is basically just going to be everything else. So this is the singular region, this is the neck region. Why is it a neck region? Because it's the region that sort of, for every point here, if you sort of rescale on the distance to the singular set, it always looks like a neck region in the sense of how people usually think of these things for bubble trees, right? So it'll always look like Rn-4 across this cone on every scale if we go into it. So this is the simplest notion of a neck region. It's singular. And let me complicate this just a teeny bit to the smooth case. So instead of having our cross-section, which is, because this is where most of the complications come in, I'm afraid. So instead of having a cross-section, which is C2 cross Z sub 2, let's take a Ricci flat approximation to that. That would be a Gucci-Hansen, right? So that there's this Ricci flat 4-manifold, right? It's on the cotangent bundle of S2. If it's scaled down a lot, it looks really, really close to C2 cross Z sub 2. So you're just thinking of it as a small approximation of that, but you've got some central 2-sphere floating around here. And I want to, again, just cross that by, I want my total space now just to be this cross Rn minus 4. So now it looks pretty much the same as the last picture, but there is one difference. If I try to cover this in a way that's kind of analogous to up here, I want sort of a smooth region and a non-smooth region, one has to be a little more careful. The singular region is no longer just some set. It's really a collection of balls because you've got to cover all those 2 spheres if you want everything else to look like this sort of smooth crossing up there. So what you can do to cover your ball is, here's your sort of approximate singular set once again. So this guy's right. Is we can just basically take any covering we want as long as we make sure it sort of always contains your central 2-sphere inside of it like that, right? So here's some collection of balls, xi, ri, and we can write B2 once again as being inside some n union S, where S now is just going to be some union of, I'm going to say, closed balls, and N is just going to be everything else again. And for just definition's sake, I sort of want to take all these center points of all these balls and just call it C for center. This is a general neck region. The point is that you don't know on a smooth space, right? It may look like a singular set at some scale, but if you go down enough, it may stop looking like a singular set. And one has to take this into account in the analysis. So you just cover the whole thing by some collection of balls. So instead of just sort of a nice singular set, you have a collection of balls that approximate the singular set, right? So our centers now are an approximate singular set. So the general definition is just exactly this. So we say that a neck region is some subset of a ball. I usually say 2 just for nice whatever reasons. And we call it a delta neck if the following is true. There's some collection of center points, xi, just like the centers of these balls here, and some radius function, so it's a collection of balls, not just centers. So that if we throw out, I mean, n is up here. It's everything except these balls. And it needs to satisfy the following. The covering shouldn't cover too much. It's a Vitali covering, right? Sort of standard assumptions about coverings, where we don't want to recover this point 80 billion times. It seems silly. This is really the heart of being a neck region, right? Is that if we look at any of these center points, and if we look at any radius between the ball and up to 1, then we always look close to a guy like that. We keep looking like a singular set on all scales. It always looks like Rn minus 4 cross R4 quotient something on all scales. This is why it's a neck region in some sense. So our balls, I mean, it can't be so, I mean, this is basically saying our ball has to cover the central 2-sphere. Right? If it's so small that it doesn't cover the central 2-sphere, you've lost that property and you don't want to do that. Your neck region is supposed to cut that out. This is on a smooth manifold. Yeah. I mean, the paper does a metric space version, but I do smooth here. There's no reason to not. And the last condition, which is going to look funny, let me just say why it's important. This would be a bad definition if I say skip this ball here. Well, what if I just had the first 2 definitions, but I threw this ball out? Then I'm in some sense not covering the whole singular set, and that's a problem. Because there would be a point where the regularity scale, the harmonic radius if you want, is basically 0 right here. But its distance to the singular set, which are the ball centers, is some positive something. And you don't want that. So you want to make sure that you've actually covered the whole singular set the way the picture's being drawn. You haven't skipped a ball, right? That's what N3 guarantees. This is one of these, if you think 10-minute moments, right? It becomes clear. That's what N3 is sort of guaranteeing. So for the rest of the talk, just think of C, the center points, as being like an approximate singular set, so that whenever we talk about neck regions, we're just talking about something that looks vaguely close to Rn minus 4 across a cone on all scales. Okay, so what? Oh, this is just this example, but done in 2 lines instead of 10 minutes. Holy mackerel, I'm going slow. Okay, so what's important about this example? Because this is somehow, I mean, the motivation for what we're doing. So there's an important concept here that comes up a lot, and that's the packing measure with respect to this collection of balls. So we look at the measure, mu, which is the sum of Ri to the n minus 4 times the Dirac delta at that point. I think I stole the name packing measure from Jeff. I forget what we were calling it before, but that was a much prettier name. So what is this roughly, right? I mean, this is saying that if C is an approximate singular set to this n minus 4 singularity, it's saying mu is approximately the n minus 4 Hausdorff measure on it, right? That's what mu is. Like, if we went all the way down to S up here, mu would really be like the n minus 4 Hausdorff measure on that set. But since it's a collection of balls, this is approximately the n minus 4 Hausdorff measure. And what are the most important properties about this? So first off, it has bounded n minus 4 measure in this example, right? I mean, why is that? Basically because our covering here is really just a Vitali covering of a ball of radius 1 and Rn minus 4, right? That means that this sum has to be finite automatically, because every Vitali covering of the ball of radius 1 and Rn minus 4 has that bound. And more than that, if you actually looked at any ball at all, you have an Alfors regularity associated to this measure. So if this, again, thinking of this as being like the n minus 4 Hausdorff measure of Rn minus 4, on every single ball, this measure actually has an Rn minus 4 upper bound and lower bound. The lower bound is coming from the fact that we're not skipping and having holes here, right? That's the really important reason we need that third condition there. So for the silly example anyway, this is kind of clearly true because we're just covering Rn minus 4 by this. And the last point that we really want to point out is that if we look on the neck region, so that is, we've thrown out this approximate singular set here, you have your desired curvature bound. I mean, why is that? Because a Gucci-Hansen has some L2 bound, right? As you start to scale it in, right, what happens? It starts to accumulate near the singular set, and it becomes kind of 0 outside of it. So that is to say, we have not just an L2 bound, but a small L2 bound everywhere. And what we really want to say is that all neck regions have these properties, right? This is the hard part of really the theorem, is to say that all neck regions look like this. So actually, there's really 2 questions to ask about neck regions at this point, so things like this. I mean, in terms of the who cares factor, we need 2 things. 1, good properties about neck regions, so like what we just said a minute ago. And 2, there should be lots of them. Like if I define a neck region as literally being a cross product, I could prove all kinds of stuff about it, but who really cares? They don't exist, right? So we need to know there are a lot of neck regions in our space, and we need to know that we can control the neck regions. So let's start with how to control the neck regions, and then we'll come back to there being a lot of them. So our main theorem is just exactly what we just said a second ago. It says that if you actually have any neck regions, so something that sort of from a covering point of view looks like this, then it is actually true that your packing measure, so the approximate n minus 4 singular measure coming from your center balls, has Alfors regularity bounds, upper and lower, depending just on dimension. And that if we're outside the singular set, you actually have an L2 bound on the curvature. Let me point out the subtlety of this, because I mean that condition 1 there is basically equivalent to the n minus 4 finiteness of the measure of the singular set, right? So, I mean, this is really the hardest part of the whole theorem. It's tricky to prove this. I mean, the n minus 4 finiteness of the singular set is actually very easy once you have this result. So all the work from today will mainly be on this. And this is what I just said about the fact that it's the basis for the n minus 4 measure, as well as the rectifiability, but that comes more in the proof that we'll see. And the second point tells us that our L2 estimate that we want at least holds on neck regions. So basically, if we threw out the singular part and just looked at the smooth part, it's actually going to have an L2 bound. That may seem not useful, but we'll see in the next theorem why it is useful. Among the points needed to prove this will basically be a new superconvexity estimate on harmonic functions. Yeah, go for it.
So one crucial thing besides this, but behind this L2 estimate on Riemann squared is the fact that in this dimension the cones are flat.
That's actually true. Absolutely. Absolutely.
But once they're flat, then a naive thing would be you have epsilon for a bunch of annuli and it still adds up to infinity.
That's the problem.
The key point?
We'll get there.
Okay.
We'll get there. At the very least, I will say in 100 words why that's true. And if we really have time, which I think is unrealistic, we'll do it better. Okay. I mean, essentially, it's the same thing for the finite measure, too, right? I mean, why can't that kind of sum up, even though it's like a Reifenberg set, right? Why can't it sum up to infinity?
Yeah.
Okay. So that's the structure of a neck region. Now the point of there being lots of neck regions. So the next theorem says the following, and this is sort of the next major point of the theorem, of the main theorem, the next sort of mean point. So the next theorem is a decomposition theorem, and it basically says that every point in our ball of radius 1 or our manifold, whatever, lives either in a neck region or in an epsilon regularity region. So it's even better. I mean, it either lives in a region that's very close to Euclidean space smoothly, or it lives in a neck region, and that you can control the number of pieces you need in a very effective way to cover your space. So more precisely, it says the following. We have a space, we have bounds on the Ricci curvature, and we have a lower volume bound. And then for every delta, deltas are a parameter for our neck region, just sort of saying, how close to a cone this thing looks like. We can cover our ball of radius 1 by a whole bunch of guys, some balls, R sub B, and some neck regions in sub A, where the following hold. Well, the neck regions are neck regions, fine. The ball regions are epsilon regularity regions. There's a definite lower bound on the harmonic radius. If it's Einstein, this is just saying the curvature is scale invariant small, right? That's how you should think, right? Don't worry about what that means. It means you're close to Euclidean space on these balls. That's how you should think, smoothly. And the most important and the hardest part by far of this estimate is the third point that says that the number of balls in this covering has an n-4 content bound. If we sum up all the radii to the n-4, then we have a uniform bound. And in some sense, why is this important? Well, just to get some fuel for this, right? I could cover my entire ball by epsilon regularity balls. It's a freaking manifold, right? You can always go small enough and it looks like Euclidean space, right? I could cover everything by just Euclidean balls, but I couldn't do it while controlling the number of balls that well, right? It's just wrong. So this is going to somehow be the main point. In fact, that content bound there is very much related to the n-4 packing measure estimate from before, we'll kind of see. And this is what I said about on epsilon regularity balls. Just think of the curvature as being scale invariant small. I mean, it's as close to Euclidean space is how you should think. And that the content estimate is the important aspect of this. Yeah, I won't really say anything more about the proof of this. It's basically, once you know the structure theorem, you have to know it first to prove this. It's a complicated covering argument. Actually, there's 5 different types of balls. You decompose your space, and you basically sort of find some natural way of decomposing. Think of every possibility. You get 5. You decompose your space into these 5, and then you keep redecomposing all the others until all you're left with is this, and you keep track of the errors. So let's just call it done and not worry about it.
What do you mean all the others?
Well, I'd have to be careful. I mean,
other places that you didn't cover yet?
Well, no. Basically, I mean, you don't know this is true yet, right? So you start off by trying to find a more obvious way of covering your space, but it gives you more possibilities that don't look like just those 2. And then you have to take those other possibilities and recover them, right? I could do this more precisely, but not if I wanted to say more about anything else. It's technical, but not that bad, right? Okay. So now the main challenge of the paper by far is to prove these structure and decomposition theorems. But instead of jumping into it, what I want to actually do is at least convince so that you have a global picture of what this proof looks like, convince you how to get the L2 bound once we have them. Right? So let's pretend like we have the decomposition theorem. We can actually split our space up into these, and that we understand neck regions the way I've claimed. Then why do you actually get an L2 bound on the curvature on your manifold from this? It turns out to be, pretty easy, so it gives you a nice global view of what's happening here. So let's do that quickly. Okay, So let's try to prove our L2 curvature bound. So the first step is simply, well, I mean, decompose our space. We have a decomposition theorem. Let's decompose it. So we have a ball of radius 1. And by the decomposition theorem, we can split this into two types of pieces, either neck regions or epsilon regularity regions. If you want, these are like necks and bubbles. The epsilon regularity regions are like, when you get a bubble out of a neck. So we've split our region into necks and bubbles. And of course, if we wanted to bound the L2 curvature on the whole ball, we can obviously just try to sum up over these two regions instead, right? It's enough to look at the sum of the L2 bounds on the neck regions plus the sum of the L2 bounds on the epsilon regularity regions. But what can we say about this? Well, our structure theorem claimed starting with the epsilon regularity balls. That's a better one to start with. If you're on an epsilon regularity ball, you have the following scale invariant estimate pretty trivially. You have that the L2 of the curvature on your ball actually has a scale invariant bound. That means, r to the 4 minus n times the integral of the curvature squared is small. Just rescale it to a ball of radius 1. You have a bound of this thing of some epsilon. Rescale it back down, you get that r factor, right? So nothing too fancy happening there. And again, if you want, you can think of this, if this is Einstein, you actually have a pointwise bound that looks like that, so all I did was integrate it. On the other hand, this is the much harder thing to prove. If you're on a neck region, then our neck structure theorem claims that we have a scale invariant bound there too. So again, we could take this neck region, we scale it to a ball of radius 1 where we claim that we actually said epsilon, but whatever. Where we claim that there's an L2 bound on neck regions, and then again scale it back down to a ball of radius r, and this is the scale invariant estimate you get. So we know this for every neck region. So let's just plug the silly estimates in, right? So you look at the integral of the curvature on the ball of radius 1. You bound this by summing the curvature over neck regions and bubble regions. And by what we just said, we can bound that by some constant times the sum of RA to the n minus 4 plus RB to the n minus 4. Right? But what was the main point of the decomposition theorem? That we didn't have too many of these balls in the decomposition. Right? That's exactly the statement that's bounded. And that's it, done. Right? So fine. So the point being is that the structure theorem then the decomposition theorem are clearly the hard part. Right? I mean, I mean that this is what you want to show, and if you can show that, the rest kind of follows out fairly easily. Okay, so probably I'll spend the rest of the time now kind of outlining the proof of this neck structure theorem. Just for convenience sake, let's state it again because it's probably slipped most of our heads. So recall what we have is just a manifold with some bound on the Ricci curvature and a lower volume bound. And we have some neck region, which is to say it just kind of looks like this. It looks like Rn minus 4 across a cone. And we've covered the approximate singular set by some collection of balls. So we have our approximate singular set C, which are the ball centers. And the structure theorem claimed that on the one hand, the packing measure, the approximate n minus 4 Hausdorff measure of this set, had Alfor's upper and lower regularity bounds. And we claimed that on the neck region up here, we actually had a small L2 bound on the curvature. So there's three basic points out of all this. So we have to show the lower bound on this packing measure. We have to show the upper bound on the packing measure. And we have to show the L2 estimate. And all three of these are actually quite different, and they require different ideas to actually deal with them. So we kind of have that written here just for recollection's sake. Here's our neck region. So what I'm going to do now is the following. I'm going to go through each of these 3 points and kind of say, in 100 words or less, how the proof kind of goes by, and then we're going to start focusing on one to do more carefully. This proof is slowly going to get more and more technical in case I haven't lost you yet. We actually haven't entered the bad part yet. So we're still in the outlining phase. So let's first outline the lower bound. Why this packing measure here should have a lower bound on its sum. It will come in point 3. That's exactly right. Because the L2 curvature estimate, right? What if I didn't have that, just morally? What if I missed these balls? My L2 curvature estimate couldn't be right. Right? Because I would have had to have sort of hit this region here, which has a lot of L2 curvature a priori. So that will actually appear directly in the estimate for the L2 estimate.
Is that important for the upper Hausdorff bound?
The lower bound?
Yeah.
No.
So the other direction. Wrong direction.
No. Wait. It actually is. Actually, I take that back. We'll see it.
Okay.
It actually is. It doesn't by other methods, but it is by this one, in fact. So let me just say yes. So let's just focus on the ball of radius 1, because it actually doesn't matter. I mean, take any ball of radius r, it's the same argument. So how does this go? So roughly speaking. So remember, how did we conclude it for the example? What we did was we took these centers, we projected them into Rn minus 4, because they were basically all living on Rn minus 4, and we said we had some vitality covering of the ball of radius 1 and Rn minus 4, and therefore had to have gotten our upper and lower bounds. We kind of want to mimic that idea. It's just more technical because we don't really know how these things are scattered. It's a Reifenberg set, and that's all we really know right now. But what you can start with is you can start with some, I mean, the set of centers here is Gromov-Hausdorff close to the ball of radius 1 in Rn minus 4. That just kind of follows from the definition of a neck region. So we can use some distance functions and find a 1 Lipschitz map. That's a Gromov-Hausdorff map. So it's going to project our ball centers into the ball of radius 1 basically any way you want, as long as it's 1 Lipschitz, which is very, very important, the 1 Lipschitz part here. In the example, right, it's literally projection to Rn minus 4, right? That's how you think. But you can build one of these maps in a million ways on a general space. Pick your favorite. So this induces, once again, a collection of balls now on Rn minus 4 instead. Right? And if we're trying to mimic the sort of how we got our estimate here, what we really want to say is that this induced collection, after we've projected the centers to Rn minus 4, actually covers a ball. Right? If we have any collection of balls in Rn minus 4 that covers a ball, so like if we have any collection here that actually covers something, then this sum must actually have a lower bound. Like that's just a Euclidean space fact, right? That this must always be true. So this is the hard part, to actually show this. To actually show it basically requires two things. One is basically like a discrete Reifenberg type theorem. So there are these sort of, I mean, it's going to be, I mean, how to think. This collection of balls here, unioned up, looks roughly homeomorphic to the ball of radius 1 in Rn minus 4, right? If we fuzzy ourselves out in a discrete sense. So what we have then, a Reifenberg map would say this in a slightly precise way. Because the way we want to think is that we want to view this as being roughly homeomorphic to the ball of radius 1. We have this 1 Lipschitz map now into the ball of radius 1 that maps it into there. If these were smooth mappings, right, there's a degree argument. It says that this set here and this mapping is looking roughly like the identity. So it's degree 1. So if these things were actually smooth maps, we could use a degree argument and say it has to be onto. Right? And to make this precise, you can use basically a discrete version of a topological degree argument with a discrete Reifenberg argument. So you can make this rigorous, is all I'm really saying. You can view this as being like a mapping from a ball to a ball and use a degree argument. I say I'll discuss this more, but I won't. The upper bound. So the upper bound's analysis, right? The lower bound was not analysis in some sense. The upper bound will require a lot of analysis. So what we're going to do is we're going to start by looking at a splitting function on our ball of radius 2. Now, I'll say what this is precisely later. Jeff talked about it a couple days too. It's just basically a Gromov-Hausdorff map that happens to be harmonic. That's how you should think about it. Right? So we know our space is close to Rn minus 4 across a cone. So there's basically a Riemannian submersion in a Gromov sense into Rn minus 4. I want a harmonic version of this. So we'll start with that. And we're going to prove a new estimate on it. We're going to show this mapping. So this is some harmonic mapping here. That's going to look roughly like you know, roughly like the identity mapping here in some approximate sense. But we're going to show that on most of these centers, that it's going to be 1 plus epsilon close to, it's going to be a 1 plus epsilon by Lipschitz map onto its image into Rn minus 4. So that we're essentially going to get a by Lipschitz equivalence of this covering with some covering into Rn minus 4, at least for most of this set. Let me point out the subtlety of this. This is roughly like a codimension 4 set. Even if, I mean, by classical ideas, Even if you assume the L2 curvature bound, assume it. Assume we know it. It's what we're trying to prove, but whatever. Assume we know it. You can't prove that by standard techniques. It's too refined. You can't get epsilon understanding of a code-emission force set by what would become L4 estimates on the Hessian. You can only get M-4 minus epsilon understanding. So the estimate going on here is somehow actually it's stronger than just the L2 estimate. It's a little bit more refined. This is, yeah?
What do you mean by Lipschitz? I mean, dimensions are different. What does this mean exactly?
I mean that you've got your set here is that a bunch of discrete points, right? They're going to have image points. And I'm saying on these points, it's going to be by Lipschitz, right? So this is looking roughly like Rn-4, and it'll actually be by Lipschitz like Rn-4 on most of it. So we'll need a new superconvexity estimate for harmonic functions to prove this. This requires the two-sided bound on Ricci, by the way, not just a one-sided bound. The proof will actually be induction on scale, but I won't get to it, so let's not worry about this. Okay, finally, curvature estimate. So the last outline, and then what I'll try to spend the rest of the time after we discuss this is going back to this upper bound, because I'd like to talk about the superconvexity estimate. That's somehow the most interesting aspect of this, I think. So how do we get the curvature estimate? First point is that we automatically have to know the upper and lower L-force regularity bound. So this was his question. A priori, before we can actually estimate this. And the main lemma is going to be the following, which is going to look unfortunately technical. So it's saying the following. Pick a point in the neck region. Y. Let's look at a ball that's on the scale of the distance to your singular set, right? So here's a ball of radius r. So that, the distance from y to your singular set here is basically 2r, right? So this is inside the regularity region is the point, at some scale invariant distance. Now let's ask, what's the integral of the curvature here? So then what you can do is you can look at a quantity called the entropy. Actually, you can look at the volume ratio or basically any good monotone quantity you want on Ricci spaces. The entropy turns out to be technically the most convenient, doesn't matter. But it's an energy is what you want to think of. And to measure the curvature here, then what you can do is look at the part of mu that's roughly close to this. And you can integrate the energy drop along mu, along this part of mu. And why is this useful? It's because at every single point here, the sums of all the energy drops is small, because you're always looking close to a cone. So if I took every single scale invariant ball that existed on this neck region, I sum them all up, and I plug that estimate in, and what do I actually get? I get that it's the integral over mu of the sum of all energy drops, which is pointwise, which is bounded by some small something times the measure of mu. This is sort of why I was saying, so actually in the proof, the L2 bound and the upper L-force regularity bound, they actually have to play on each other a little bit. Okay. I do have better notes for this, but we will probably not get that far. All right, so clearing our heads and starting over now. So what I want to do with the remaining time is try to discuss the upper L-force regularity bound a little bit, at least enough to tell you what the main computation is. That's sort of interesting. This seems not realistic to me, actually, but we'll try it. So the key concept here is that of a splitting function. So let's recall what this is. Jeff discussed this, so hopefully this is a little bit in our heads. So a splitting function is just the following. It's a mapping on a ball of radius r, for which it's harmonic. Its gradient is always close to delta ij in some integral sense. Its Hessian is small in some integral sense. And we can take the gradient to be bounded above by 1 pointwise. And roughly speaking, this is an analysis way of saying that your ball looks close to RK cross something. Because if you were actually RK cross something, then the projection map to RK would be one of these maps with delta equals 0, right? And essentially the statement here is that conversely, this is basically Cheeger-Colding now, right? That if you're close to looking like RK cross something, then there is such a map that actually exists. So this is what relates geometry to analysis. And we like this because we can control analysis and then use the analytic control to then control the geometry. So it's a way of detecting Euclidean factors. And so let me state the main result on splitting functions, one of two main results. So let me state some assumptions. So again, as always, we have a neck region, just some collection of covering like this, so you're always looking like a cone. And now we've got some splitting function on this ball. Fine. And here's sort of a semi-tricky point. We're going to assume for the moment an Alfor's regularity bound, upper and lower. I'm choosing my constant b here to be different than the a that appears in the theorem for a reason. So assume some Alfor's regularity bound, maybe not the one that we actually want to prove eventually holds. Right? So in the end, we want to say that b is some dimensional a of n, so that this b3 is redundant. But in the proof, we don't know this yet. We can't do that. So we're just assuming some bound. Then the main theorem is the following. So imagine we have a space with a lower volume bound and a small Ricci bound, and which satisfies these three conditions. Then if we look at the collection of our center set, right, this is like our approximate singular set, right, our ball centers, then there's some subset C epsilon of it, which by condition 1 is most of it. It's in the packing sense, most of C epsilon. And so for most points inside the set, you have two things. And let's even just focus on the third one for a moment. You have that the mapping from C epsilon into Rn minus 4 is actually by Lipschitz, right? So this is rigorously what I mean by Lipschitz, is this guy here. So if we take 2 points in this set, and we look at their image points and look at the distance, which is all that is, and then relative to the original distance, it hasn't changed very much. And this is true for most of the points. So let me point out why this is so interesting. So let's pretend like this is true for a minute, right? Then what can you do? You can take your original collection of balls that are up here, right? And then let's restrict it to C epsilon and look at their images in Rn minus 4. So this up here is a Vitali collection, right? So you know, balls of radius Ri over 10 or 100 or whatever disjoint. But then we've mapped it into Rn minus 4 to get a new collection. But by this, it's still a Vitali collection. So we've taken a Vitali collection and now mapped it into a Vitali collection. That means we have some Vitali subset of the ball of radius 1 or 2 sitting inside I guess R the way that, no, yeah, that's right, sorry. Inside the ball of radius 1, which means we automatically have an upper bound that's dimensional. So if we sum the Ri, so that we look at the measure, the sum of the Ri's to the n minus 4 from this set, it has to be bounded dimensionally. So up here, you're assuming some upper bound, which may be much, much worse. But then as soon as you know this is true, you've now pushed that bound down and it's smaller than you thought it was. So even though you're assuming a bigger bound, you actually get a smaller bound immediately out of this. Roughly how this goes in practice is that this is why you prove by induction. You go to a very small scale where you know your Alfor's regularity holds, like say the ball of radius Ri itself. By definition, the packing measure, it holds there, right? Then imagine you're on some ball of radius R and you know that the final upper bound for the Alfor's regularity holds. Well, then you can go to the ball of twice that size. Now, you can't prove the bound you want there, but by a bad covering argument, you can prove a worse bound. It's only dimensionally worse, but it's worse. But then you can plug it into this and see actually it's not worse, it's just as good as it was to begin with. And therefore, this lets you keep going up in radii and eventually get it for all radii. Okay. 5 minutes. Let me think about how to approach this. Okay. So the main estimate here is going to be the following. So to define so this is the most important estimate that's been written down. So sort of in the spirit of to every new theorem, there's a new estimate. This is the new estimate to the new theorem. So what it's saying is the following, and that there's a lot of words there, I know. So we're going to define a wedge region. So what is this? So take some point, one of your center points x. Then roughly the wedge region, I mean, this is a wedge, right? So ignore the actual statements there. What that's saying is that our wedge region, W R of x, is this here, right? It's the part of this wedge between, I guess, R over 10 and 10 R is the way it's being said, right? So this piece of the wedge here. And what we're going to do actually is estimate on these wedge regions here. So these are away from the singular set, right? And the final estimate says the following. It says that if you integrate over all of mu, and what you're integrating is the sum at each point over all wedge regions of this scale invariant L1 estimate, then you get something small. And why is this important? It's because so this factor here, that's right there. Well, what is that controlling? So a scale invariant L1 Hessian estimate here is basically telling you how much your function is changing from here to here. That's what it's stopping. So what this theorem here is saying is that for most points, if we summed up at that point how much our function changed from here to here, from here to here, from here to here, and so forth and so on, it's small. I mean, if you think for a little bit, this is basically by Lipschitz. It's saying that our function really hasn't changed from what it looked like up here to all the way down to your radii itself. And if you're careful about it, this is actually what Lipschitz comes from. Okay. So to prove the estimate, you want to first turn it into something more interesting and more reasonable looking. I mean, it's being phrased that way for the application. When you say it that way, that this is sort of how you apply it to get your Lipschitz. I mean, let's say it in a way that's more obvious to actually prove the estimate itself. That this takes a little bit of structure, I'm afraid. I'm going to assume Ricci flat, basically, because it throws a lot of terms away that I don't have to worry about. It's not a big deal. So what I'm going to do is consider the Green's distance function. So this is sort of like a higher dimensional sort of generalization of what Kolding and Minakazi consider in some of their papers. What we're going to do is look at the Green's function whose support is our approximate singular set, mu. So we're just going to solve for that now. And then we're going to solve for a function b defined that way. Why define that way? Well, imagine this is actually a product, like the top guy, and our mu is actually the singular set here, so this is just the n-4 measure there. Then b here is actually the distance from r n-4 factor. You can check this, right? So this b here is sort of a smooth approximation to the distance function. Actually, you could take any smooth approximation to the distance function you want here. It doesn't have to be the Green's one in our case, but it makes life easier. So now, it's not actually the distance function, of course, on this set, but as long as you have some Alfors regularity bounds, you can say it's close to the distance function. You can say it's approximately equal to the distance to C, and that its gradient is approximately pointwise equal to 1 everywhere. And now what we're going to define is the following. So what's this set b equals r? It's basically this set here, right? It's basically the ball of radius r around the singular set here. So we're h of r, we're looking at where we're integrating along b equals r. One can think of this as this r inverse should be like r times the average over b equals r if you want. It's like the average of the L1 Hessian here times r. It's the scale invariant Hessian along the set of points whose distance from the singular set is 1, r, sorry. And if you check carefully, basically, the estimate we want, ignore those lines, because I have 3 minutes, just ignore them. It's a Dini estimate, if you're careful about the estimates. Controlling what we want to control in our wedge regions is actually the same as just saying that we can integrate, if we look at the scale invariant H1 estimate here, and we don't just integrate it here, but we're basically summing over all scales of it, where we're integrating it times 1 over s. If that's small, that's basically equivalent to our wedge estimate. So this is what we really want to prove. And now, why is this useful? Basically, because of this. So if you write it this way, you can prove that this sort of superconvexity. It says that, this left-hand side here is basically a scale invariant second derivative, right? Because you want to kind of go on scale here. So we have the scale invariant second derivative. And if the left-hand side, the right hand, what direction are you guys looking? right-hand side is 0, bigger or equal to 0, you're basically saying you're scale invariant convex for H. But now ignore that second air term over there and just look at the first guy. This is like a superconvexity. This is much better than convexity. It's not just convex, but if H got big, it became really, really convex. And this is somehow the key to sort of decay and growth estimates. So if you pretended, for instance, like all your balls were the same radius, you would get this pretty cool looking estimate. It would say that actually your scale invariant Hessian actually behaves like this. It's got some scale invariant bound, at the smallest radius, some scale invariant bound at the bigger radius, and it's decaying polynomially in between. That's more than strong enough for what you want to prove. It turns out the different ball radii is very, very painful here. But if you're careful, you can at least get exactly, no more, no less, exactly what you want out of it in the general case. It's not that strong of an estimate, but it's strong enough for what we want. Okay, I'm done.
In that small epsilon for the L2 thing, you had a sum of absolute values, but then can you drop the absolute value so it's just the whole thing? And
it's a monotone quantity. That's you're talking about the curvature.
So
exactly.
Okay.
That's exactly the point, right?
Yeah.
Thanks.